Wayne Green on asynchronous meteor observations. Never heard of an asynchronous meteor?
We don't have a watch. Speechless. Need a break, or is it? Oh. Just there we go. Cool deal. Hello, can you hear me okay? Yes, I guess I can hear me okay. That's all that's important, right? My name is Wayne Green. I'm with the Denver Astronomical Society, the Boulder Astronomy and Space Society, the Longmont Astronomical Society, anything that has to do with the Deep Space Exploration Society. Rodney Howe, who was supposed to be here a little bit earlier, was going to speak somewhat on that. At this meeting last year, we got to talking a little bit about when we observe a meteor, how do we find out where it was? What are our chances of recovering one? And what do we do with all the data that we have left over for all the ones that we never recover? So I decided to put together a little chalk talk about the prediction of debris fields and sort of the refinement of some of the characteristics. Oh, am I being filmed too? Yeah, okay, yeah, okay. Oh, okay. Hi there. So, yeah, I'm one of those guys. You know, put my hands in my pockets, I can't say anything. But anyway, so the net result of all of this was I decided to resurrect a technique that I had put together back in about 1974 when a bright meteor came in through Central Florida. How many of you guys know Hal Povenmire? He drugged me out of bed and forced me, for some reason, I don't know, back before I knew better, to actually figure out where this meteor had landed. Now, the meteor observations that I were given were pretty much there from the public, from policemen, from airline pilots, and from Hal, who was cursing and swearing. Because he had just set up a nice, beautiful camera network to look for meteors, and he had gotten in his chair to get ready to watch for the meteors, and a brilliant light appeared, and he figured the cop helicopter had flown over and shone its spotlight down on him. And he whips around to curse at the police helicopter and notices this minus 12 bolide, fireball coming through the atmosphere. And so he was able to pick off a couple of points. We got some reasonable data. Now, this was back when I was an undergraduate, just getting started. I checked out a book and learned about spherical astronomy to solve this thing. And let me tell you, there's a lot of problems in the mathematics using spherical trigonometry in order to deal with solutions of problems with very small angles. Despite all of that, Lake Tohopagalaga, my nice red pen here, is about 10 miles, maybe 12 miles long. You'll notice there's a nice roadway around it. Well, Hal rounded up a bunch of interviewers. They went, this happened about 9 o'clock in the evening. They interviewed everybody that was out on the back porch having a nice beer, waiting for, or enjoying the evening. And everyone said, yes, we saw the meteor, and they pointed at the lake. So if you're ever going to go bass fishing in Central Florida, please drag a magnet for that stony meteorite, and we'll see what we can't find in Lake Tohopagalaga. So I turned that program, I figured I was going to have to do this again, so I turned the program into about 2,200 lines of Fortran, and then took a few more courses in mathematics. The next approach was to come up with a vector-based approach. But one of the motivations for this was a club called the Astrogator Astronomy Club. You can see their name right here. We used to get together. We were a bunch of kids, at a children's museum, and we would go out in lawn chairs in the middle of the night, despite all the perverts that are supposed to be out there, and we would observe meteors. And NASA was interested in these data at that time, and we had our little star charts, and we would mark where the meteors went, and essentially doing a meteor network, just like you're familiar with, except nowadays we do it with CCD cameras. In that whole thing, we learned our constellations with binoculars. We got probably a few variable star observations in your database. And all of this was developed an intense cohort of kids, 5 of which went on to get PhDs, one of which is named Dr. Mike Reynolds. Many of you recognize his name from the Meteorite world. He's also, I think, the immediate past director of the Association of Lunar and Planetary Observers, active in IOTA. There's that IOTA word again. So he gets around. He's worse than I am, I guess, in terms of joining things. But the most important thing there, I think, to remember is that when we were kids, we were observing meteors with our eyeballs, and it was a captivating problem. Fast forward to modern times, we have started ourselves a little group, which we're informally calling ourselves the Mountainside River or Telescope Makers, because the Riverside telescope maker title has been taken. So, and what I've noticed is it's really, I hope it's not a flash in a pan, but it's really developed an interest in building stuff and getting out and doing stuff. And if we build it, we'll get around to using it. So with this meteorite recovery project, one of the first things we ran into was the same topic that we had talked about here a couple of, or the session immediately before this one, about the mathematics, the conventions, and so forth that goes into building a meteorite recovery station. We also decided, without really being able to consult too many people, to re-examine the engineering aspects behind building the meteor camera network. And that immediately took us into some of the interesting design flaws, if you will, of security cameras. What is an inexpensive fisheye lens? How do we deal with weather? Some of us who are out observing at night, there's a big movement in my area because I live in Colorado and it gets pretty dang cold, okay? So we're all moving into little domes. Well, when you're inside a dome, you can't tell if it's getting cloudy. If you've got a nice meteor camera watching for meteors, you can also check to see what kind of cloud conditions that you have. You have to have some control for this thing. A small, inexpensive microprocessor buys you that. So while we're at it, what we've discovered is if you go down to like Harbor Freight and buy yourself, I have no stock in Harbor Freight, if you buy yourself a small non-contact IR thermometer and you go out at night and you just hold it up and take a temperature of the sky, you get a pretty decent estimation of what the sky characteristics are. If it's kind of wet, you're going to see temperatures about like ambient, maybe, you know, something like say in my neighborhood, maybe 0 degrees C. I might see temperatures maybe 0 to -2, -4. On a really good night, and we have them, despite the rumors to the contrary, I have not been able to get a temperature reading from this non-contact thermometer. It comes back and says low. So that means that most of the energy is going out of the atmosphere and very little of it's coming back. And that's when I get excited. You know, as long as the moon isn't twinkling because of the wind, then I'm in pretty good shape. You tie all of these requirements together, and what you wind up with is a pretty decent little device that you can hang outside of your observatory, because we need baselines on these things to do these meteor recoveries. And you get some benefit right here. I mean, you can go down and say, hey, look, I've got good sky conditions. I've got some clouds maybe drifting over here. Maybe I'll decide to do my project over on this side. So there's a lot of good benefits that come out of building one of these stations. However, what I'm here to talk to you tonight about, or this afternoon about, is a little bit more about the coordinates and the mathematics that's involved. So I'm going to have to walk around on you just a little bit here. But if you will imagine, let's see, half of you guys are sitting over here, and you have, looks like about 30 meteor stations running. Half of you guys are sitting over here, and you've got about your 30 meteor stations running. There's a bunch of guys here in the middle. So if I look at the atmosphere, think of it like this ceiling up here. It's about anywhere from 75 kilometers to about 135 kilometers tall. As I begin to look over, though, and I go all the way down to the horizon, how far can I see before there's no air? So that was a question that we had to solve. The next question that we came into is if you take some photographs and you guys take some photographs, how can we agree on what points in order to make our range finding estimations based on? Okay. So if we use a camera, then what we're doing is we're taking a photograph. We've got distortions. We have this beautiful distorting ball up here. Okay, I just noticed that. And so what we wind up with then is we have to come up with a function that will map those positions, those sky positions, back down onto our CCD so that we can turn around and reutilize those for other things. Part of the problem is that we live on a rapidly rotating fluid ball. So we're an what are we called? An oblate spheroid, right? And the oblate spheroid has differences. So there's a long laundry list of reference geoids that you can use. All of us in this room, with the exception of Olivier here, probably uses the WGS-84. There's equations that you can use to convert your latitude, your longitude, and you have to be a little careful with your altitude. It's a geodetic altitude. But you can get an Earth-centered X, Y, and Z coordinate back out of that. So at this point now, I am a XYZ point, and I'm standing in an enormously huge spherical coordinate system called the sky, with right ascension and declination. The old guys, what they call them, navigators that used the sextants, what they would do is they would essentially measure the zenith angle down to a star. And that's all they really work with. They would draw an enormous circle on the Earth. They would take 2 or 3 of these. Where these intersections occurred essentially was a point in the direction. And they could then determine, they could work that backwards, and they could determine their position fairly accurate. And you have to remember that 1 nautical mile at the equator is roughly equivalent of 1 arc minute of resolution. So when I say we're working with small angles, precision then becomes the watchword. We have to do some analysis to figure out what that's going to amount to. Here's an example of a circle, the spherical sky coordinate system, superimposed on this grossly overdrawn ellipsoid. You get about a 0.2 degree, what is that? What's 2/10 of 612? 12 arc minutes, 12 nautical miles of error at 45 degrees of latitude. If you're going to go out and try to find a meteor in the middle of Lake Tehopagalaga, the whole thing's only 12 nautical miles long, you want a little bit better resolution than that. So what we have to do then is we have to find a way of marrying these 2 coordinate systems together to get the job done. So we talked a little bit about maximum distances. The further out you go, and remember we're using tiny cameras, right? So if you shrink things down, you have a meteorite. My model meteorite, let me get this up front here, turns on at 75 kilometers, burns out wherever it's going to burn out. It's going to travel some distance. We'll take a look at that here in a second. I've got 480 pixels out of my 640 by 480 camera. If I put my circle in the middle of that with a fisheye lens, that means that I've only got 480 pixels of resolution. If I'm looking way out at a great distance, then I'm going to have a lot of error the further out that I go. So bear that in mind for just a moment. So it's using simple trigonometry, and since this is going to be published on the web, don't scribble these down. What you'll find is that at a 75 kilometer height above the Earth's surface, this is a radius of the Earth, which is about, 68, 70 kilometers or so. Then what you find is that this distance to the horizon, where the first light of the meteor would appear, is about 908 kilometers. That's a significant distance. If I'm in Wyoming, if I'm looking right along the horizon and I see that dinosaur killer come in, because it's going to have to be that bright to get through all that atmosphere in Denver's light-polluted skies that Bob Stensel hasn't been able to turn the lights down on yet. So what we have to get to is we're in a situation where that's very, very far away. People tend not to realize that the scales of some of these meteor distances are that way. If I come up just 10 degrees in elevation, then my distance drops to 510 kilometers. And if I come up to a 30 degree, which is an interesting number, you'll see why I chose that one in a minute, then that means that any meteor that I might see with a camera that's looking at all the sky above 30 millimeters, above 30 degrees of elevation, then what I see then is something that's only 144 kilometers away. That's pretty close. That's almost in my backyard. If I see a meteor directly overhead, the one that's going to hit me in the top of the head, then it may be as near or far as 75 kilometers away. So that's actually fairly close. Now, Scotty had done some interesting work earlier. I just found out about this last night, and it'll be in the paper, or be in this presentation, is he managed to get some meteor data during some of his occultation events on one of these things where he had these cameras strung out over a very long baseline. Just to put things into perspective, this is a graph. Incidentally, most of the graphs that you see, with the exception of one, were prepared using data that I've collected and put into data sets so that I can use them for modeling and for my research, and plotted using Python and using Matplotlib. So this is actually, this distance here is probably about one of the longest meteors that would ever get hit on the Earth. Because remember, it's got to get into the atmosphere, it's got to start to burn, it's got to go a great distance, and chances are it's going to hit the ground. Now, these can go a little bit longer, particularly the Tunguska types. Well, actually, they think that one hit now, these. But the ones that come in and actually skip through the atmosphere, those are pretty interesting. However, we're never going to recover one of those. But that's the kind of an area that you're looking for. So if you're planning an a wide area network type of thing, then you need to cover about a state, at least a good state's worth of distance. Another question, this is one that Dr. Mike had brought up, Mike Reynolds. If a meteor comes in and it has a magnitude, what are my chances of recovering it? And so I dug into some of the literature, and I came up with a number of characteristics that govern that, mass certainly being one of them, but we get the composition and the density. And there's some, now, let me stop here for just a second and remind you guys of one thing. Most of the meteors that you see, 99% probably of them, are cometary debris material. They're fluffy. They're going to burn up and turn into dust. And you can recover them. Just stand out with your hand out like this, and you'll get some microparticles of them coming down on your hand just about all night long. There's a number of these things hit the atmosphere. Every meteorite that we have recovered, with the possible exception of one, has been of asteroidal origin. So in that case, we're dealing kind of with two animals. The asteroidal orbits that are associated with things are nice kind of characteristic things to go for. But there's also meteor characteristics that go buried in our data that we don't necessarily go back and recover. Okay? This is a graph that I prepared using an equation that was developed by the Schmidt camera groups and also by Peter Jennison's that shows the relationship between the mass, shown here is the log of the mass along the bottom, the initial velocity at the contact with the atmosphere, and it gives you a magnitude readout. You'll notice that this slope, which is the density, is a little bit higher in a lot of ways than the velocity. So when it comes right down to it, mass is responsible for the magnitude of your meteor. So there's a good correlation there. And intuitively, it makes sense. That minus 12 that came into Central Florida is certainly gave us the opportunity to recover one of these guys. Did I go the wrong way? Nope, I'm going the right way. Okay, so one of the things, too, to remember is that air distorts images because we've got refraction, that process that's going on there. For you modelers, there's a nice little thing from the United States Naval Observatory called the Novara C library package that has an equation, a formula in there. You call it up. It'll give you the refraction based on your zenithal distance, or if you just do a little bit of arithmetic on your elevation. And we'll take a look at a curve here in a second about that. There's also things in the air itself. So when we talk about air mass, under photometric conditions, we can get away with it. But if we've got humidity, we've got a lot of other things, and we have a lot of particulates in the atmosphere, we're going to get a lot of absorption. So that cuts down on some of that. A bright meteorite overhead may appear to be a dim meteor at a distance, but that may be a significant meteor, so just don't go throwing that one out of your data. Okay. This is a slide that I got out of some NREL solar data. The gray line represents the solar energy at the top of the atmosphere, and the dark line represents solar energy that they've measured here on the ground. In terms of photometry, we tend to think about these water barrier lines. Matter of fact, the filters are named for these gaps where in the water absorption portion of the spectrum where light can make it all the way down to the ground. We're also conditioned to think in terms of a black body, in that all of the energy that's available can never exceed essentially the black body temperature at a particular spectral frequency. So you always see things quoted in terms of Janskys per hertz. That's not necessarily the case with meteors, however. Dr. Jensen was observing one night with a really nice spectrograph, and they were just really happy about their dim data, and this very rude, very bright meteorite got in the way of their data. So in this graph, what I want you to pay attention to is that he reports things in ADUs, or analog units here. Notice these very, very, very bright lines, and notice where their spectral intensities fall. This is one of the highest sensitivity areas of these small security cameras. Now, the security cameras are represented in terms of lux, which has to deal with how the eyeball works on things. I tossed in a graph of Vega here, which is based on Cruz's model. This is a numeric set of tables. Again, I just plotted this out for reference. So I've got a nice reference Vega for my magnitude terms. This is a different kind of physics. This is not a black body physics that's related necessarily to the meteorite. This is a black body physics that's related to the heating of the object as it comes through the atmosphere. And that's one of the most important things that we shouldn't be overlooking. Flux is flux. We run wide open so that we can get the best signal that we can. This is a graph of how your eyeball works. It's always handy to look at your black and white vision versus your color vision. This came from the Institute of Ophthalmology. There's a group of them down here at UCSD and another one's at King's Cross College. Out of that literature, I found that there were 150 quants or photons that were necessary for visual detection of things. A lot of times what we see too in terms of these cameras is they're reported in terms of 10 to the minus 4 type of lux. What the heck is lux? Lux is essentially this integrated area within this spectral range, shown here in angstroms, so that we can compare apples to apples in terms of how people and how humans use lighting to interact with their environment. They don't speak of anything about the sensitivity of this camera out here. I suspect that 10 to the minus 4 is actually a few decimals better because of the spectral nature of that chip. Okay. Multiple station versus single station observations are important. If you only have one station, and I know there's a group here in the room that has one station, you can still make some vital contributions. What you do is you watch a shower full of meteors. Using the same techniques, running the problem backward, you can determine the radiant for that sample collection of meteors that you've seen. If you get that real rug burner that's coming in here, that dinosaur killer, and you've got multiple stations, you use the same technique, you run it forward, and you can get a pretty good estimate of your debris field. And there's some questions that I want to follow up on here in a little bit about some of that. I reached into IMO database and I pulled out as many meteors as I could find, that were of use to me. They came out of the Japanese Meteor Workshop database out of IMO. They have about 3,500 meteors or so. I plotted them, and what I noticed is that they were all pretty much in the same plane here, okay? Or actually, what would that be? Same. They're spread out all over inclination. You can see that they're all closed orbits. This is the line that represents a circle where the eccentricity is 1. So I imagine this is where Earth has carved out its little niche. It's vacuumed out that little area out of this space. But one of the reasons I wanted to present this to you is because you'll notice there's a sparse number of data points in there. We certainly have the capability of driving up the number of characterized meteors that are available. Keep on moving here, but running a little bit behind, I imagine. One of the things that we come up with is that when we take an image, like I mentioned before, all sky, fold it down onto 480 pixels, then we have to come up with a way for each pixel to go back into our coordinate system. The best way to do that is take a number of photographs fairly close together. We're shooting video after all. Sum these things together, and what you'll get is you'll begin to get the dimmer and dimmer stars. You can measure the distance. You can come up with an equation, essentially an x squared and a y squared type of equation, system of simultaneous equations. I wasn't about to solve it. I typed into Mathematica, help me solve this thing. It gave me a nice piece of Python code then that helps me map those positions back into their right ascensions and declinations. I don't really want to spend a lot of time setting my meteor station up. I want to get it soundly put in place, put it there, and let it watch the sky, make sure it doesn't wiggle around or shift in any way. Then I can build my transfer function, and what I'm doing is I'm turning an x and y pixel coordinate over into an altitude and an azimuth. Now what the altitude and the azimuth does for me is it saves me the bother of having to have an accurate clock to decipher right ascension and declination through our angle back into the same thing. I can just do my transfer function all in one step. I get the result that I want, because I want to have a vector that's centered at the center of the Earth that points in the direction of that meteor. And somewhere along that vector is where that meteor particle was. Now, if you guys are sitting on this side of the room, excuse me, let me walk out of the field of view here, and I'm looking, say, off in this direction, I'm going to see a meteor pass across the sky in this way. Now, where is that meteor? It's somewhere between the end of my laser pointer and the top of the atmosphere. If I'm from your guys' stations over here, 5 minutes, then what I wind up with is a projection that goes along in this fashion. So somewhere in this big volume of area is where that meteor actually occurred. All I need are the angles to make that work. Zip along here a little bit. I mentioned atmospheric refraction. You'll notice at 80 degrees, so this would be 10 degrees of elevation above the horizon, I'm at 5 arc minutes of refraction. So maybe I don't need a fisheye lens to be playing down here in the muck. Remember that when you see the moon on the horizon, it hasn't risen yet. You're actually looking over the horizon in order to see that. This is a chart of air density. In the references at the back here, you can find where to get these data. I plotted it out, and it got really thin here at 40 kilometers. So I went ahead and replotted it on a log scale so you can get an idea of about what the mean free path, we're actually talking about the distance between molecules in this regime. When a meteorite comes into the atmosphere, it will not heat up and it will not begin to glow until its cross-sectional area exceeds the mean free path of the molecules up there. So the density of the air means something. The really big guys turn on at higher altitudes, burn longer, last longer. The little tiny guys have to go deeper into the atmosphere before they experience any heating. So from an operational aspect, this was taken in my backyard. Step over here for just a second, get my orientation. This is a tree that's 30 degrees. I stood at the location of the camera and with my cheesy little sextant measured that distance. So from this point to this point was 30 degrees. You can see that I'm fighting a lot of distortion, a tremendous amount of distortion using a fisheye lens. So if I'm going to ignore everything below 30 degrees, why am I using a fisheye lens? I should switch over and start using a wide-angle lens. It brings things a little bit closer. It means I have to have a bigger density of my collecting stations. Okay? And this is some measurements. I'll leave the slide in the presentation so you guys can refer to it. Again, you can see this was also a full moon that evening. A little bit of flare events, nasty street light. Have to have a talk with that fellow. Okay. So what we did is we developed a transfer function that matches the pixel x and y immediately into zenithal distance and an azimuth force, so we can begin our analysis right off of the bat. Saves us a lot of stuff. Skip some of the stuff about that. Skip some of this. We talked a little bit in this meeting about the CCD television format. And you'll notice that there's always this little gap in there that corresponds to like the horizontal and vertical retrace times of old televisions. That acts as a chopper in the same way that the old guys did with the mechanical shutter. So the extra piece of data that we're getting out of this, both in terms of the deceleration for the meteor we're trying to recover and to work backwards to get that initial velocity and some of the velocity characteristics, fall right out of our data based on the fact that we're using the television. 2 minutes, okay. We get over here to some of the more interesting slides here. This is a meteor that I reached into, second meteor I pulled out of the database. In the old days, what the guys tried to do was they tried to find out that point right there where it turned on, the part maybe somewhere in here where it turned off, and you notice I'm using some thin terms. And they also looked at the point where the meteor reached its maximum intensity or some fraction thereof. This little fella had 2 bright spots on him. So I pulled up my favorite program, DS9, drew a region across here, expanded it out a little bit to add some pixels together, and I got this nice light curve from this meteor from a data set that was in the International Meteor Organization's database. And then what I proceeded to do was to do the absurd thing and fit a 31-degree polynomial to this data. It's amazing that the polynomial didn't blow up. At this point, we have some artifacts, so you can't really get at what you want. What do I got, about 2 minutes? 1 minute. 1 minute, okay. Get down here to some of the punchline. Okay, this was some of Scotty's data. This is the most important slide. What you could do then is you could take 2 of these points, any points that you may choose along this meteor. Each one of these would correspond to a pixel from your camera. You can build yourself a plane. From my station, I pick any 2 points along this line that I might wish, and I can make my own plane. I intersect those planes. I get a line segment. I can have about 2,000 segments to play with. I wind up with 2,000 segments to do the regression for my recovery curves. Run the regression backwards, I get the radiant and orbital characteristics. I run it forward, and I get the debris field. And with that, I think I will finish.
Okay, we'll take one question. One question. Anybody?
Talk to me later.
Okay.